Welcome to NPTEL. Myself Dr. Jayanto Das from Department of Metallurgical and Materials Engineering, IIT Kharagpur. I will be teaching you advanced materials and processes. Today we will continue our earlier discussion on advanced processes. So, these advanced processes are required because there are several demands in terms of materials and properties. These properties could be the intrinsic properties or extrinsic properties. Now, if you closely look into these nano structured materials, and if we like to scale up those nano particle or nano materials, then I may start with let us say 200 nanometer finer particle, or maybe let us say something like 1 micrometer, which have been prepared some of these sol gel processes. However, those as prepared powder need to be consolidated. Consolidated means I am talking about compaction, and the theoretical density should be or the sintered density or the compacted density should be close to the theoretical density, then only we will be achieve good mechanical properties, otherwise the material will be microporous. So, these are the challenges. Now, porosity could be reduced if we anneal during sintering or temperature of sintering is higher. But if we increase the temperature of sintering and time of sintering, then grain growth we cannot stop, which basically means we have started with a nanocrystalline powder, we end up with a microcrystalline powder. So, there is no benefit at all, and that is why this processing technique and their very critical parameters are optimized, as well as newer processing technique has been evolved. So, if we look at the scaling up process, and sintering is one of such process where we start with powder and we make bulk solid out of it. So, there are two major type of sintering are possible. One is pressureless sintering, that is a conventional sintering process, whereas there are pressurized sintering, means during sintering process we apply pressure. Now, let us look at the pressureless sintering process. In that case, the process has many different types. So, here I show you 6 different types. One is reaction sintering, means during sintering itself the reaction goes on and we take, or some heat may evolve during that reaction. So, that has been utilized for sintering purpose. So, I need less energy for that particular reaction, because there is already some reaction going on in the material which is being sintered. Such a technique is named as, let us say, self propagating technique or conventional reaction sintering. Any reaction goes on. So, that is a typical conventional, but let us say if you take some iron and alumina and then react with each other, let us say then Fe2O3 and aluminum, they can react together, and so it will basically make your a self propagating type of synthesis. Once the reaction has started, you do not need further activation energy in order to propagate the reaction. So, this is one type of self propagating high temperature synthesis process. However, one should estimate how much calorie has been evolved due to the self propagating propagating nature per unit mass and so on. On the other hand, the pressureless sintering process has a thermal plasma assisted sintering, or maybe we can send a microwave so that particle can be bonded together. Okay. So, these are also conventional pressureless sintering. So, all these technique has been evolved for sintering without application any hydrostatic or external other kind of pressures. The last technique along this pressureless sintering is that atmospheric sintering or maybe inert gas. So, we can sinter under a vacuum, so that the oxygen partial pressure will be very less, or otherwise we can also put some air into it in the chamber where sintering process is occurring, or maybe we can put some nitrogen, argon, inert gas and so on. So, it completely depends on the material that you are going to synthesize, whereas any dissolved nitrogen can affect the properties of the material or not. So, depending on the inert atmosphere is chosen. So, atmosphere should be chosen in such a way, so that it will not degrade the properties of the material after the sintering process. On the other hand, we can conduct this sintering process under pressure. This pressure could be two different types. What I want to mean that I can apply pressure by using some gas molecule or using some solid compaction. Means solid means I have a die, and the die we apply mechanical forces, so that powder can be compacted. So, in that way means by application of solid compaction, there are three other technique has been developed, like hot pressing. So, hot pressing means at higher temperature we apply pressure, we basically sinter the compact. On the other hand, we can also go for the spark plasma sintering. So, spark plasma sintering means the assistance of plasma that make or assist the formation of the neck between two particles, powder particle, using a plasma, and then we sinter. So, the third category of this is the ultra high pressure sintering. Here the pressure applied pressure is very high. So, you need a very good die for that. On the other hand, we can go for gas compaction, means the pressure is applied using a gas that is surrounded around a chamber, and that chamber compressed the whole powder. So, this pressure goes in a isostatic manner, that is called as a hot isostatic pressing or high pressure gas reaction. So, there is a reaction involved, that is the high pressure gas reaction sintering. However, among all these technique, we are mostly concerned about the pressurized sintering, because it can yield a very high quality of the compact and by retaining its particle size, the initial particle size. So, one is the solid compaction technique like spark plasma sintering, and let us say the hot isostatic pressing. So, we will discuss these two techniques which are very important for us. Now, for spark plasma sintering, SPS process involve a dynamical non-equilibrium processing phenomena. Means, so the SPS processing technique which is possible sintering or sinter bonding at relatively lower temperature and in a very short period. So, you can see the shorter the period basically assist us that to avoid the grain growth. Now, by charging interval between the powder particles, what I want to mean? So, if I have two powder particle, if I have two different powder particles, so I can make some charge and apply some electrical energy to there, and we can create a localized plasma in that region, so that they can be bonded together. So, particles with a electrical energy and effectively applying a higher temperature spark plasma generated at an initial stage an electromagnetic field and the Joule heating by continuous on off DC pulse high electric current with low voltage. So, a schematic is shown here and an image of such a spark plasma is shown here. So, let us say here there are dies which are lying at the top and the bottom, and they actually act as a electrode. So, these are the punches. So, you can see these are the punches which act as the electrode. So, this one is the upper punch and this one is the lower punch. So, powder is placed in this region. So, powder is first place and this is a sintering die which kept the powder intact, and then we apply some higher pulse of DC pulse, electric field and low voltage. So, current here is very much important because we like at a lower voltage high current to be passed, so that we can create a plasma in between two particles. However, along this way, so these are the punch electrodes that are connected. So, these are the punch electrode that are connected and we apply some also pressure or load. And here the whole sintering process involve is a SPS, this is a DC pulse is applied. Along with that, the positioning is important, the environment, operating environment, we need some water cooling, so that during that plasma the die may require some cooling effect. At the same time, we need some thermocouple and some hole, so that we can monitor the temperature of the process. So, this is somewhat very much important parameters that we need to also look at. However, the mechanism of SPS or spark plasma sintering process is also very much interesting. So, if I microscopically like to show you that there are different particles. So, this is a various types of different powder particles that are very close to each other, and the current basically passes through the powder particle. So, this flows in this way, and here this is another flow. So, we will have a chance that due to this current passing inside the particle, we will have some Joule heating. So, this Joule heating can be estimated by I square into R. So, the resistivity into the current, that square term. So, if we on and off the DC pulse current path, then in the powder particle itself the current will flow and they will assist in the formation of such a neck due to the localized Joule heating. So, SPS process is a electrical sintering technique which applies on and off DC pulse voltage and higher current from a special pulse generator to a powder particles. However, when this sparking basically occurs, the higher temperature field with sputtering phenomena that are generated by spark plasma and spark impact pressure eliminate the absorbed gases and oxide film and impurities that is existing on the top of the surface of these powder particles. So, what I want to mean that there could be very small oxide or some other kind of adsorbed gas film. However, we can eliminate it during that pulse and application of the physical forces. Now, the action of this electromagnetic field that enhances a high speed diffusion of the atoms due to high speed migration of the ions actually, because we have already created a plasma in the localized region between the particles. So, this on off pulse that basically assist to generate the spark plasma. On the other hand, it generate the spark impact pressure and it induce a Joule heating as well as it enhance the thermal diffusion. So, this is the whole process that basically govern the whole SPS sintering technique. Now, we can see some microstructure or real microstructure of the initial neck formation. So, in the left hand side here image, you can see that these are the two powder particle and it is a image has been taken at the very initial stage of a neck formation. So, you can see that there is a neck already formed. So, once the neck forms, then definitely the atom will migrate from a higher curvature to a lower curvature region. So, that will basically assist with a convex and concave type of curvature and the migration will continue. So, with that there will be a expansion of this neck area. So, there will be more particle will join and at the end we can get such kind of highly compacted, that is a start of the plastic deformation and flow, because we already have the powder particles that are very close and if we apply pressure then we can eliminate these kind of internal pores and so on. So, this is a case that I have shown you in case of a copper 10% tin particle size of 45 micrometer. This is the initial particle size, average particle size. The scale here is 5 micrometer. So, for this particle it is something like 10 micrometer diameter. So, the application of the pressure was 29 megapascal, temperature was only 773 K and the holding time is 2 minutes only. So, within a very short time the voltage is only 3.9 volt, but the current is very high. So, like 850 ampere. So, this is a very high current actually. So, spark discharge appear in a gap of the contact point between the particles. So, these two particles there is a spark discharge, there is a Joule heating, that is I square R, and the local high temperature state, that is a discharge column of the several 10,000s, that is around few centigrade, thousands of centigrade are generated momentarily. So, it is like a real spark phenomena appear in a very localized region, and this causes evaporation and melting of the surface, and if there is any vaporized atom, then they will again go and sit in the neck region actually. So, if there is at all any evaporation of the atom from the surface, and they will always like to go from the curvature difference. So, these are already discussed phenomena in the nanomaterial classes. Now, the necks are formed around the area and contact point between the particles. Now, there are also other techniques that are very much important, but before going to that, we must think that whatever I have discussed so far, that is with the conductive type of particle. Now, if I like to sinter a ceramic material, means I have particle, they are ceramic. So, ceramic are very bad for conduction, electrical conduction. Can we simply compact using that spark plasma sintering? That is the question. So, yes, it is possible. So, usually all different kinds of material can be possible. So, starting from different metals like iron, copper, aluminum, gold, silver, they are automatically the electrically conductive material. However, the ceramic oxide like alumina, mullite and zirconia. Mullite is basically a compound of alumina and silica. So, magnesia, silica, titania, they are carbides, nitride, boride. We can almost sinter any of these high temperature materials by using this spark plasma sintering, and the effective product is also very high. However, in case of a non-conductive sample, the specimen is self heated in addition to the external heating by an increased amount of electrical current that passes through it. So, to sinter a ceramic material, we have to pass a much higher current, and at the onset of the temperature, that is related to the material resistivity behavior, with temperature the specimen becomes sufficiently conductive to allow a high electrical current passage, and significant acceleration of the specimen heating is accompanied by a very fast sintering in a few seconds. So, with that actually we can sinter a non-conducting, means I am talking about electrically non-conducting material. There are very good advantages of this particular SPS technique, like it is a very fast sintering technique. The grain coarsening, which is very important aspect, is very less, and variety of materials that I have already, different classes of material can be synthesized. Compaction, sintering combined process. So, it is not a one way process, we also use some physical forces. The disadvantage is that heterogeneity in the temperature field of the compaction lead to inhomogeneity in the microstructure. It basically says that in some region the particles there are plasma, and there may be the temperature field that is localized is different in this region than this region. So, I may have a larger grain size in a localized region, I may have a finer grain size in other region. So, this is like a microstructural inhomogeneity, that is a small disadvantage we have to accept. Now, the application that I have told, that pure let us say metal, tungsten carbide and aspheric glasses, lens mold, and let us say different nitride and oxide composite can be done, or let us say different sputtering target material, fabrication of large side metal compact can also be done. So, in such a case, let us say the silicon nitride alumina composite that is shown here, you can see the outer look of those product with the top lid and hollow cylinders that has been produced by spark plasma sintering. Now, the second process is the hot isostatic pressing. So, the hot isostatic pressing involve a simultaneous application of the isostatic pressure and elevated temperature to a workpiece, which result in the workpiece that is usually powder becoming consolidated. So, in that case the pressure is applied as a gas. So, let me explain you the process with a schematic. So, please have a look at the first schematic that is shown here. The schematic is shown here. So, this is let us say the initial shape of the powder that is going to be conducted. Okay. Means I have powders inside this chamber and this is a envelope. This is a initial envelope that contain all the powders and I have actually the gas which is outside. Okay. So, the pressurized container is here, okay, gas container is here. Now, I apply pressure so that the gas molecule will hit the surface of this envelope and it will be compacted at a final shape of such. Okay. So, initially it was like this and after that it was like that. So, from all the sides the gas molecule hit the envelope and assist the compaction of the powder. That is basically the process called as hot isostatic pressing. So, the applied pressure goes to the material through a gas, usually it is a inert gas, and since it is a uniform pressure that goes from all the sides to the envelope, it is called as a isostatic pressure. Now, driving force for the adhesive let us say or to achieve densification is associated with the reduction of the surface area and surface energy of the pore. The isostatic pressure arises from the molecule or atom and gas colliding with the surface of the object. Each gas atom is acting as an individual hot stage and they are hot forged between the particles. So, under particular processing condition, the gas atom may moving at a velocity of around 900 meter per second. So, this is a very high speed, the gas molecule goes and hit the surface and let us say something like 10 to the power 30 collision event that goes on per second, which is per square meter. So, this is a very high value of collision event. So, in that that basically assists to get a very high compact density and a schematic of such hot isostatic pressing chamber is shown here like a furnace here. This is a furnace that provides the heat. We may need assist of a forced convection or not, that completely depends on the user choice. However, for this gas handling we may need some vacuum. So, initially we put some vacuum and then we put some inert gas may inside and some electrical circuits are there. So, this is just a layout of the cover lift and so on. So, this is a total schematic of such a hot isostatic press. Now, the typical hot isostatic pressing here the temperature almost reaches in case of aluminum and its alloy, since aluminum has a melting temperature of 660 degree, the yield stress at room temperature may be something like 100 megapascal, and if they are nano powders or nano crystalline then it may reach up to 600. And let us say if aluminum alloys contain some nano intermetallics or very fine size intermetallics, then it also can increase the strength. So, the typical heaping temperature is like a 500 degree centigrade and pressure of 100 megapascal. So, that is good enough. For alumina composite, so we can apply a much lower heaping temperature because we have pure aluminum, and so heaping pressure you need a little bit high in order to move those alumina. Let us say for copper, the melting temperature is 1080 degree centigrade, and let us say the yield stress it varies between 60 to 960. So, we apply some temperature around 800 to 950 degree centigrade with a pressure of 100 megapascal. So, there are also many hydroxyapatite, titanium aluminides and ceramic superconductor steels, all of them can be heaped, and the process parameters are also listed here. Now, the advantage and disadvantage of this hot isostatic pressing is like here, the powders are consolidated at a much higher density and much lower temperature, that I have already shown you in my earlier slide, and highly complex shape can be processed because we apply gases which apply the pressure. So, we first put the pressure into gases, and that gas causes the isostatic pressing. So, if I have an envelope that can goes into a very complicated geometry, the gas can go everywhere and can apply the pressure. So, that is why very complex shape can be generated, and heap parts have a homogeneous density, whereas high gas density facilitated heat transfer and brittle material can be processed. Now, the disadvantages are the high cost of the intricate shape that cannot be formed, and small scale production of this heap. So, we have some disadvantage because of the cost and the small scale production. However, the removal of micro and macro porosity in case of nickel or cobalt based super alloy, we can apply this hot isostatic pressing, and high speed tool steel that is close to theoretical density can be achieved, and synthesis of intermetallic compound like titanium boride or exothermic reaction can also be done. And the benefit you can see very clearly that this is the yield stress of a as cast material, and another one is the heaped material. Okay. So, this is a nickel aluminum bronze we are talking about. So, the heap product has a higher yield strength. Now, if we go for ultimate tensile strength, that is also higher, that is 670 megapascal. The elongation to failure is also high because we have very less porosity and material is almost defect free. So, all these process, the heap process shows a much beneficial effect than the as cast material of a nickel bronze, and this is another example of a alumina heaped powder kept at something like 850 degree centigrade for 12 megapascal at 1 hour. So, you can see that almost there is no porosity involved, and the microstructure is fully dense. Now, there is other technique, that is the so far technique I have discussed, they are from the powder we consolidate to make a bulk scale. However, if we have to produce bulk structure, then we can also go from or start from a bulk solid and keep on modifying the microstructure and go up to the nanoscale. So, that is like a top down process, and another technique is the severe plastic deformation. We introduce plastic deformation into a bulk solid, which basically means we introduce dislocation and defect inside it. So, there will be several microstructural mechanisms that will operate and assist the formation of the very small scale grain into the microstructure. Now, severe plastic deformation is one of the method for obtaining very fine crystalline structure of different bulk metals and alloys. So, there are typical technique like ECAP. ECAP basically means equi-channel angular pressing. So, I pass a bulk solid through a channel, and the specimen move at a particular angle, and because of that the plastic deformation is introduced. So, there is a estimation how much strain is involved, that is epsilon, which is linked with the cot of that angle of the bending. and the number of turn means how many times we pass the material through the channel, that will also increase the amount of the strain. Now, the second process is the REC. REC basically means reciprocating extrusion and compression. Now, the third technique is the HPT, that is high pressure torsion. And here also we have a flat disc, we will go into detail, and then we make a torsional strain, and definitely we can produce bulk nanostructure using this. The fourth technique is the CCDF, that is cyclic closed die forging and accumulative roll bonding, or the repetitive corrugation and straightening. So, in this case we take a bulk solid and simply we use such a die, and so we make a corrugated structure. After making the corrugated structure, we take a flat die and again we repeat this process by making it flat. So, the more the process this cycle goes on, we can introduce more and more strain. So, this SPD causes the formation of micrometer and sub-micrometer size subgrain that are initially coarse grain material. So, I can show you some of the schematic of such a SPD process, and you can see that by simply pressing through a SPD process like a E cap, the material is pressed through that, and we have a angle that is, let us say psi, and so the accumulated strain, that is the number of the passes and the strain shear strain that we introduce divided by root over of the 3, and that is also linked with how much angle we provide. So, we can make a direct 90-degree angle, or maybe we can reduce the angle. So, there are dies which are shown here, and if we start with such a coarse grain microstructure, yes, due to the elongation of the microstructure, then we can produce very finer structure. So, a rod is basically forced through the die, and it basically sheared and extruded emerged rod that same diameter with what is started with, and it can be reinserted several times, and so that the die deform, but reinserted so that we can introduce the more number of turns. So, here we can achieve a grain size in the range of a 100 to 500 nanometer. Now, the second severe plastic deformation process is the high pressure torsion. In that particular technique, the two ends of a bar. So, here there are two plunger, and we have the sample here, and we rotate this plunger in the opposite direction. Okay. So, if I have a disc, then at the circumferential region I will introduce maximum amount of strain, because the more strain is achieved at the r theta. So, the accumulated strain here in the material can be estimated by the logarithmic of the shear strain that is evolved, and the shear strain is linked with the radius divided by the h. So, h is the thickness of the disc and r is the radius of the disc. So, if you place this, the shear strain in the surface near to the surface is very high than the center. So, we expect a microstructural inhomogeneity or gradient of microstructure along the radial direction. So, that is also represented here. So, this is like the hardness of a as started material which was a annealed, and then we applied 0 turn. So, the annealed sample has a lower, however, the hardness will keep on increases, and then if we go to a much higher number of turns, then you see that the hardness will be fluctuated at the center, the hardness will be less, and if we increase more number of turn, then almost hardness is getting saturated. So, this is a micro hardness distribution across the diameter of a aluminum disc at a pressure of 1 gigapascal. So, the total number of revolution was 8. So, this is also a very novel technique of producing such kind of nanostructured material. I show you just 3 example of such microstructure. Here this is number of turn is 5, here also number of turn is 5, here also number of turn is 5, but the effect of pressure it is 1 gigapascal, 3 gigapascal and 9 gigapascal during high pressure torsion. So, the scale bar here is 1 micrometer, 0.2 micrometer means 200 nanometer, and here this is 100 nanometer. You can see that by application of a higher pressure, we can easily reach to a nanoscale grain by the same number of turn by increasing the applied pressure. So, this is such a novel technique that we have many different process parameter to control the resulting microstructure in a very bulk scale. So, this is another top down process of synthesizing nanostructured materials without compromising with the any kind of grain growth, where there is no question of such a grain growth, and we can process such a material, novel material much easily. With this, we stop our discussion today. We will continue the discussion in the next class. Thank you very much.